So the last time we met, we actually covered the material from 6.1 and 6.2, but I'm going to just go back and do one or two examples from each section before we go back to go on to section 6.3. So I wanted to look at two problems where you have to find the radius of convergence and the interval of convergence. So let's look at this. I can't remember what example this is going to be for us. So let me go back and see. This is example 5. Okay. So we want to find the radius of convergence and the interval of convergence. So the radius and interval of convergence. Okay, so the first problem is going to be, so the first one is going to be the sum n equals 0 to infinity of n times x minus 3 to the n divided by 5 to the n. And I'm hoping I didn't do this one last time. No, I didn't. Okay. All right, so when we look at this problem and we want to find the radius of convergence and the interval of convergence, anybody have an idea of what test they may want to use for this? What test would you like to use for this problem? Hello? Anybody there?
Would you use the ratio test?
Okay, I can use the ratio test. So what do I need in order to use the ratio test? I need to do what? I need to identify what AN is. So AN is n times x minus 3 to the n divided by 5 to the n. Okay, so what else do I need, Maria? For the ratio test. For the ratio test, what else do I need? Okay. Oh, I cannot hear you, Maria. So if you're speaking, I could not hear you, no. I don't know, your sound must have gone out. Can you type what you want me to know? What were you trying to say? Oh, she may have logged out.
Dr. Lott,
Yes.
would it be possible to take the limit of, or we take the limit of from n to infinity a plus the absolute value of an plus 1 over an?
Very good. Okay, so we also need to identify an plus 1. So an plus 1 is n plus 1 times x minus 3 to the n plus 1 divided by 5 to the n plus 1. Okay, so we need to then compute the absolute value of an plus 1 over an. Okay, so that means I'm going to take this term, that's an plus 1, and then I'm going to divide by this term. Okay, and I need that in absolute value. All right, so then that's going to give me the absolute value of an plus 1 over an is going to equal n plus 1 times x minus 3. So yeah, the whole thing is an absolute value. N plus 1 doesn't need to be an absolute value anymore, it's positive. But the absolute value of x minus 3 to the n plus 1 has to be in there. And then I get over 5 to the n plus 1, that's positive, so I don't need absolute value. Then I'm going to get 5 to the n, and then I'm going to get down here, n, and then the absolute value of x minus 3 to the n. So I get these two values, that times that. In abs, oh, I already did the absolute value. Okay. So now I get the absolute value of an plus 1 over an. As you can see, you end up with n plus 1 over n. I have the absolute value of x minus 5. And then I get x minus 3. And then it gets divided by 5. Okay, so now number 3 is to find rho. So rho is the limit as n approaches infinity of the absolute value of an plus 1 over an. So that's the limit as n approaches infinity of n plus 1 over n times the absolute value of x minus 3 over 5. All right, so what's that limit? Well, this part here is just 1. So that part just goes to 1. So then I just get the absolute value of x minus 3 over 5. And then in order for it to be convergent, that has to be less than 1. So therefore we get the absolute value of x minus 3 has to be less than 5. Okay, so that says -5 is less than x minus 3. All right, so this is x minus 3 is less than +5. So therefore we get -2 is less than x is less than 8. Okay, so this, what did I call this before? I gave this a name. Anybody remember what name I gave this?
Integral of convergence.
Okay, but it's the preliminary one. Very good. And I forgot right here to say that the radius of convergence was 5. So from here, the radius of convergence is 5. Okay, so why do I call that the preliminary interval of convergence? Why is it preliminary? Why aren't I done?
Is it because it's not an interval notation?
No, that's a good statement, but that's not the reason. The reason is because I have to still check my endpoints. So I have to check my endpoints. So we have to check what happens when x is equal to -2 and 8. Okay, so let's go back to the original series. So the original series was this. So that's my original series. Okay, so now that I have the original series, what I want to do is I need to see what happens. So the first I'm going to check at x equal to -2. So let's check that first. So we get the sum n equals 0 to infinity of n. I'm going to get -2 minus 3 to the n divided by 5 to the n. And that gives me summation n equals 0 to infinity. And then this is going to give me -5 to the n over 5 to the n. So that's going to give me -1 to the n times n. And that series looks like 1 plus, it starts off with 0. So I can look at this series. And this series looks like 0. Then I'm going to get -1 plus 2 minus 3 plus 4 minus 5 plus 6, etc. So for this one, I can just look at the limit as n goes to infinity of the nth partial term, which is -1 to the n times n. Just as I look at the nth partial term, that sum, that's an, and I know right away that that is not 0. So therefore the series diverges. That's just by using the nth term test of divergence. And then at x equal to 8, I get the sum n equals 0 to infinity of n times 8 minus 5 to the n, 8 minus 3 to the n, over 5 to the n. And that's just the summation n equals 0 to infinity of n, and that also diverges. So now I know that it does not diverge, it does not converge at, okay, Jadeja, it does not converge at -2 and 8. So therefore my final interval of convergence that's -2 up to 8. Okay, so it only converges inside that interval, but does not converge on the outside of that interval. Okay, any questions about that?
Did you say that, you applied the nth term test for the last part?
Yes, the nth term, so the nth term test of divergence, if you remember. So let's talk about that. The nth term test of divergence. So if you have a series summation n equals 1 to infinity of an, or I can even make it start at 0, doesn't matter. So I have a series that looks like that. Okay. The nth term test of divergence says if the limit as n approaches infinity of an is not equal to 0, then the series diverges. Okay, so when I look at the limit of this, that thing doesn't even really have a limit. N can go to infinity, but this n itself is going to positive infinity. That thing's not going anywhere near 0. And then this limit is n goes blows up. So that one blows up. So that one, the series diverges as well. So we use the nth term test of divergence. So you have to know all 12 tests to be able to do the test on the power series. Okay, any questions about that? Okay. All right, anything else particularly y'all want to see for this stuff, or I'm going to go ahead and do an example with the looking at the derivative and the integration of the series. Okay, so what we talked about last time was we said you can combine power series, we can add them and subtract them. We can multiply them. We don't divide them at all. We can differentiate them. And then we talked about integrating them as well. Okay. So here's a problem. It's a different type of problem. So it asks you to identify this. I think this is a tough problem, but it's a good example. Identify this function. The function that's represented by this power series. So it is f of x is the sum n equals 0 to infinity of -1 to the n times x to the 2n plus 1 That does not look like an n. That looks like a half of an infinity. Divided by 2n plus 1. Okay, so as I start to write out this series, when n is 0, I just get x. When n is 1, I get x cubed over 3. When n is 3, I get, no, when n is 2, I get x to the 5th over 5. When n is 3, I get x to the 7th over 7. So as I'm looking at this, I can honestly say to you, this does not look like something I recognize. But I do know that, let's try to differentiate this. So take the derivative of this. So let's consider its derivative. So its derivative looks like 1 minus x squared plus x to the 4th minus x to the 6th plus dot, dot, dot. Now that does look familiar to me. Okay, that looks a little familiar. I can even write that as f prime of x is the sum n equals 0 to infinity of -1 to the n times, well, I'll write it like the opposite, negative x to the 2n over, nope, there's no over. That's it, x to the 2n. Nope, that's not right either. I need x squared to the n. I think now that's right. So let's see, if n is 0, I get 1. If n is 1, I get negative x squared. That looks good. If n is 2, I get x to the 4th. So that looks right. Okay, so I'm going to rewrite it because now it looks to me like a geometric series. Okay, and I meant to tell you back up here, -1 less than or equal to x. This thing is only valid between -1. Oh, between -1 and 1. Okay. So it looks like a geometric series to me, but I'm used to seeing a geometric series starting at 1 to infinity of minus x squared to the n minus 1. So now it looks definitely like a geometric series. So if that's a geometric series, I know that for me, r in this problem is negative x squared. And I also know this geometric series converges only if the absolute value of minus x squared is less than 1. So this is only going to converge when the absolute value of x squared is less than 1. Okay, that's when I know it will converge. Okay. All right. So since this is a geometric series, and I'm assuming it converges for this region, that is -1 less than x less than 1, then it has a sum. So f prime, which looks like the sum, n equals 1 to infinity of minus x squared to the n, I know it sums to a over 1 minus r. A is 1, so I'm going to get 1 over 1 minus r. 1 minus r is 1 minus negative x squared. So this thing sums to 1 over x squared. So now I know f prime is 1 over 1 plus x squared. So therefore, what is f? What is f? What's the inverse of 1 over 1 plus x squared? Hello? That's one we know. Hey, guys, y'all gotta know this.
Tan inverse.
Okay, thank you. So this is going to equal tan inverse of x plus a constant. So now we know what that series is. So that series is tan inverse. Okay, awesome. Okay,